December 2, 1942. A squash court beneath the University of Chicago's football stadium. A structure of graphite blocks and uranium rises 20 feet high. Pile 1, the world's first nuclear reactor. Physicist Enrico Fermi supervises as control rods are slowly withdrawn. Neutron counters click faster. The pile is going critical, achieving a self-sustaining nuclear chain reaction. For 28 minutes, humanity controls the power that fuels stars. Fermi calmly takes measurements while colleagues watch tensely, knowing that miscalculation could trigger an uncontrolled reaction. At 3:53 p.m., Fermi orders the reaction shut down. It worked perfectly. Arthur Compton calls Harvard President James Conant with coded message. The Italian navigator has landed in the New World. Conant asks, "How were the natives?" "Very friendly," Compton replies. "The nuclear age has begun." Within 3 years, this discovery will incinerate 2 cities and kill over 200,000 people. Within decades, it will provide electricity to millions and threaten human extinction. This is the story of nuclear energy's discovery, how scientists unlocked the atom's power, how pure research became weapons of mass destruction, how the quest to understand matter's fundamental nature gave humanity godlike power, and how we're still learning to live with what we've unleashed. The story begins not with dramatic explosions, but with invisible rays and mysterious elements. In 1895, Wilhelm Röntgen discovered X-rays, radiation that could pass through flesh and photograph bones. It was accidental. Röntgen was experimenting with cathode ray tubes when he noticed a fluorescent screen glowing across his lab. X-rays became a sensation, demonstrating that matter contained hidden properties and energies. In 1896, Henry Becquerel discovered radioactivity, also by accident. Studying phosphorescence, he left uranium salts in a drawer with photographic plates. When developed, the plates showed images despite not being exposed to light. Uranium emitted invisible rays spontaneously. This was strange. The energy came from the uranium itself, not from external sources. Something was happening inside atoms. Marie Curie, a Polish scientist working in Paris, investigated this phenomenon for her doctoral research. With her husband Pierre, she discovered 2 new radioactive elements, polonium and radium. Marie coined the term radioactivity. Her work was groundbreaking. She was the first woman to win a Nobel Prize, 1903, shared with Pierre and Becquerel, and the first person to win 2 Nobel Prizes, chemistry, 1911. Her research established that radioactivity was atomic property, not molecular, pointing toward atoms' internal structure. But what were atoms? Since ancient Greece, philosophers had speculated about indivisible particles. By 1900, atoms were accepted but thought to be solid, indivisible spheres. The discovery of the electron in 1897 by J.J. Thomson challenged this. If atoms contained electrons, they had internal structure. Thomson proposed the plum pudding model, electrons embedded in a positive sphere like raisins in pudding. Ernest Rutherford, a New Zealander working in Britain, revolutionized atomic understanding. In 1899, he discovered that radioactivity came in different types, alpha and beta rays. Later, gamma rays were identified. Alpha particles were helium nuclei, beta particles were electrons, gamma rays were high-energy electromagnetic radiation. Radioactivity wasn't just energy emission, it was atomic transmutation. Elements were changing into other elements, violating the supposed immutability of atoms. In 1911, Rutherford and his students Hans Geiger and Ernest Marston performed an experiment that shocked physics. They fired alpha particles at thin gold foil, expecting them to pass through with minimal deflection. Most did, but some bounced back at sharp angles, like firing a naval shell at tissue paper and having it bounce back, Rutherford said. This meant atoms were mostly empty space with a tiny, dense, positively charged nucleus containing most of the mass. Rutherford's nuclear model of the atom replaced Thomson's plum pudding. Niels Bohr refined Rutherford's model in 1913, proposing that electrons occupied specific energy levels or orbits, around the nucleus. Electrons could jump between levels by absorbing or emitting energy as photons. This explained atomic spectra, why elements emitted specific wavelengths of light. Bohr's model, though later superseded, was a crucial step toward quantum mechanics. The nucleus itself remained mysterious. It contained protons, positively charged particles discovered by Rutherford in 1919, but the nucleus was heavier than protons alone could account for. In 1932, James Chadwick discovered the neutron, a neutral particle with similar mass to protons. The nucleus contained both protons and neutrons, bound by a then-unknown force. Einstein's 1905 equation E equals mc2 suggested that mass and energy were equivalent and interconvertible. This meant atoms contained enormous energy. Matter itself was concentrated energy, but nobody knew how to release it. Radioactive decay released energy spontaneously, but slowly. Could atomic energy be released deliberately and rapidly? In the 1930s, physicists began bombarding atoms with neutrons, protons, and alpha particles, creating new isotopes and studying nuclear reactions. In 1934, Enrico Fermi in Rome bombarded uranium with neutrons, creating radioactive products he couldn't identify. He thought he'd created elements heavier than uranium, transuranic elements. He was wrong, but the error was understandable. In 1938, Otto Hahn and Fritz Strassmann in Berlin repeated Fermi's experiments. Chemical analysis revealed something shocking: barium, an element with roughly half uranium's atomic mass. How could bombarding uranium with neutrons produce barium? Their colleague Lise Meitner, an Austrian Jewish physicist who had fled to Sweden to escape Nazi persecution, understood. Together with her nephew Otto Frisch, Meitner realized that uranium nuclei were splitting, fission. Meitner and Frisch calculated that uranium fission released enormous energy, about 200 million electron volts per atom, versus a few electron volts for chemical reactions. This energy came from E equals mc2. The mass of fission products was slightly less than the original uranium nucleus, with the missing mass converted to energy. A tiny mass loss produced huge energy. Frisch demonstrated fission experimentally in January 1939, confirming Meitner's interpretation. The discovery electrified physics. Within months, scientists worldwide were studying fission. They made a crucial discovery. Fission released additional neutrons, typically 2 or 3 per uranium atom. These neutrons could trigger more fissions, releasing more neutrons in a chain reaction. If controlled, this could produce steady energy. If uncontrolled, it could produce an explosion of unprecedented power. Physicists immediately recognized military implications. Nazi Germany had invaded Czechoslovakia, possessing uranium mines. German scientists understood fission. Several European physicists, particularly those who had fled fascism, feared Hitler acquiring atomic weapons. In August 1939, Albert Einstein signed a letter drafted by Leo Szilard warning President Roosevelt that atomic bombs were possible and Germany might develop them. Roosevelt authorized preliminary research, though major funding didn't come until 1941. The Manhattan Project, launched in 1942, was history's largest scientific project to that point, employing 130,000 people, costing $2 billion, over $30 billion today, and spanning multiple secret facilities. General Leslie Groves commanded the project. J. Robert Oppenheimer led scientific efforts at Los Alamos, New Mexico. The project faced multiple challenges. The fissile isotope comprised only 0.7% of natural uranium, mixed with uranium-238. Separating them required enormous effort. Gaseous diffusion plants at Oak Ridge, Tennessee used miles of piping to separate isotopes by slightly different molecular weights. Alternatively, plutonium-239, created by bombarding uranium-238 with neutrons, was also fissile. Reactors at Hanford, Washington produced plutonium. Meanwhile, at Chicago, Fermi built Pile 1 to demonstrate controlled fission. The pile used natural uranium fuel and graphite moderator to slow neutrons, increasing fission probability. Control rods absorbed neutrons, allowing operators to regulate the reaction. On December 2, 1942, Pile 1 achieved criticality, proving controlled nuclear reactions were possible. This wasn't just a physics experiment. It was proof atomic energy was practical. Designing bombs was theoretically straightforward but practically difficult. A critical mass of fissile material would sustain a chain reaction. Too little, neutrons escape without triggering fissions. Too much or bringing subcritical pieces together too quickly causes premature detonation, a fizzle. Two bomb designs emerged. Gun type, shooting one subcritical piece into another, and implosion, compressing a subcritical sphere with conventional explosives. Uranium bomb, little boy, used gun-type design. Scientists were confident enough it would work that no test was conducted. The plutonium bomb, Fat Man, required implosion, which was tested at Trinity Site in New Mexico on July 16, 1945. The explosion released 22 kilotons of TNT equivalent. The fireball was brighter than 1,000 suns. Oppenheimer, witnessing it, recalled Hindu scripture, "Now I am become death, the destroyer of worlds." The bomb worked. Humanity had harnessed nuclear energy as a weapon. 3 weeks later, on August 6, 1945, a B-29 bomber named Enola Gay dropped Little Boy on Hiroshima, Japan. The bomb exploded at 8:15 a.m., 1,900 feet above the city. The blast, thermal radiation, and subsequent firestorm killed approximately 70,000 immediately and another 70,000 within months from radiation and injuries. On August 9, Fat Man was dropped on Nagasaki, killing approximately 40,000 immediately and another 40,000 later. On August 15, Emperor Hirohito announced Japan's surrender. World War II was over. The nuclear age had arrived in the most horrific way possible. The bombings remain controversial. Defenders argue they ended the war, preventing a costly invasion of Japan that would have killed millions. Critics argue Japan was already defeated and ready to surrender, making the bombings unnecessary massacres. The debate continues, but the immediate effect was clear. Nuclear weapons were unlike anything before, single bombs destroying entire cities, with lingering radiation killing for years. After the war, nuclear energy development split between military and civilian applications. The U.S. maintained nuclear monopoly until 1949, when the Soviet Union tested its first atomic bomb, aided by espionage from scientists including Klaus Fuchs. Britain 1952, France 1960, and China 1964 followed. The nuclear arms race was underway. The hydrogen bomb, developed in the 1950s, used nuclear fission to trigger fusion, combining hydrogen isotopes, releasing even more energy. The first H-bomb test, Ivy Mike in 1952, yielded 10.4 megatons, 500 times more powerful than Hiroshima. By the 1960s, both superpowers possessed arsenals capable of destroying civilization multiple times, mutual assured destruction, MAD. The world lived under threat of nuclear annihilation. But nuclear energy also promised peaceful applications. The same fission process that powered bombs could generate electricity. Nuclear reactors use controlled fission to heat water, producing steam-driving turbines, similar to coal plants but using uranium instead of coal, with no greenhouse gas emissions. The first nuclear power plant, Obninsk in the Soviet Union, began operating in 1954. The U.S. followed with Shippingport in 1957. Britain, France, and others built nuclear plants. By the 1970s, nuclear energy provided significant electricity in many countries. France generated 70% of electricity from nuclear power. Nuclear energy seemed the future, clean, limitless energy from tiny amounts of fuel. But nuclear power had problems. The technology was expensive, plants cost billions and took decades to build. Nuclear waste remained radioactive for thousands of years, requiring permanent disposal solutions that remain unsolved. Most seriously, accidents could be catastrophic. 3 Mile Island, Pennsylvania, 1979, was a partial meltdown caused by equipment failure and operator error. Radiation release was limited, and no deaths resulted, but it terrified the public and halted U.S. nuclear expansion. Chernobyl, Ukraine, 1986, was worse. A flawed reactor design and operator mistakes caused a catastrophic explosion and fire, releasing massive radiation across Europe. Officially, 31 immediate deaths occurred, but long-term cancer deaths numbered thousands. An exclusion zone surrounding Chernobyl remains uninhabitable. Fukushima, Japan, 2011, resulted from an earthquake and tsunami disabling cooling systems, causing meltdowns. Radiation release forced evacuations. No immediate deaths occurred from radiation, but the disaster reinforced nuclear power's risks. These accidents, plus waste disposal problems and weapons proliferation concerns, turned public opinion against nuclear power in many countries. Germany decided to phase out nuclear energy. New plant construction stalled and the U.S. nuclear energy's promise dimmed. Yet nuclear energy persists. Some argue it's necessary for combating climate change, providing carbon-free baseload power that renewables can't yet match. New reactor designs, safer, more efficient, are being developed. Small modular reactors might make nuclear more economical. Some environmentalists who opposed nuclear now support it as the lesser evil compared to fossil fuels. Nuclear medicine also emerged from atomic energy discovery. Radioactive isotopes are used for cancer treatment, medical imaging, and research. Millions have benefited from technologies descended from nuclear physics. The discovery of nuclear energy was pure science, understanding matter's fundamental nature. Scientists weren't trying to build bombs or power plants. They were curious about atoms, radioactivity, and nature's secrets. The applications, both beneficial and destructive, came later. This raises profound questions about scientific responsibility. Should scientists have pursued nuclear physics knowing it might enable weapons? Could they have stopped it? Once discovered, could nuclear energy be uninvented? The Manhattan Project scientists faced these questions. Some, like Leo Szilard, advocated for international control. Others believed scientists should discover but not decide how discoveries are used. That's for society. Still others, like Edward Teller, the father of the H-bomb, pushed for more powerful weapons. Oppenheimer, after the war, opposed the hydrogen bomb and advocated arms control. This made him enemies. In 1954, his security clearance was revoked in a hearing driven by Cold War paranoia and personal vendettas. His fall from grace symbolized the scientist who unleashed forces he couldn't control and came to regret. The nuclear dilemma persists. Nuclear weapons threaten extinction. 9 countries possess approximately 13,000 warheads. Treaties have reduced arsenals from Cold War peaks, but enough remain to destroy civilization. Nuclear terrorism remains a threat. What if extremists acquire nuclear materials? Iran and North Korea's nuclear programs create ongoing tensions. Meanwhile, nuclear energy offers carbon-free power as climate change accelerates. The same technology can destroy or sustain civilization. The choice is ours. From Becquerel's accidental discovery through Marie Curie's pioneering research, through Rutherford's nuclear model, through Meitner's fission, insight through Fermi's Chicago pile, through Oppenheimer's Trinity test, through Hiroshima's horror, through the Cold War's terror, through Chernobyl's disaster, through today's debates. Nuclear energy's 130-year journey has been humanity's most fateful scientific odyssey. We split the atom seeking knowledge and unleashed forces beyond our full control. We've used nuclear energy to generate electricity and vaporize cities, to cure cancer and threaten extinction, to light homes and cast shadows that might never fade. The discovery of nuclear energy proved that knowledge is power. in the most literal and dangerous sense, and that humanity's cleverness sometimes exceeds its wisdom. When Fermi's pile went critical in that Chicago squash court, Arthur Compton's coded message about the Italian navigator landing was more prophetic than intended. We had indeed discovered a new world, a world of incredible power and peril, of possibilities both wondrous and terrifying. We're still exploring that world, still learning its rules, still deciding whether this discovery will be our greatest achievement or our final mistake.